In Calculus 1, we learned about tangent lines, linear approximations, and differentials. And in Calculus 3, now we want to expand those same ideas, but to more dimensions than just the first two that we were dealing with in Calculus 1. So let's first talk about tangent planes. So a surface is defined by some function z equals f of xy, and it has infinitely many tangent lines at a particular point. So you can't say, the tangent line at that point, but what you can do is there's a plane that contains all the tangent lines that would have gone through that point. There, I just wrote that up real quick. All right, so this plane here, this surface here, will hold all of those tangent lines. Taken together, all these tangent lines will form this plane, right? So we can see another version of it right here. So you can see there's all those lines. Now, how do we come up with a tangent plane? What are the things that we need? Well, to find the equation of a tangent plane, we're obviously going to need to know the point, P, which will be an x0, a y0, and a z0. Then we're going to need the normal vector, right? So the point P is right here. Right? There's P. And we need the normal vector sticking up in the air. Oops, sorry, that's off screen. So the normal vector. N, right? Which will be some A, B, C. And then we will put it together and say that A times x minus x0 plus B times y minus y0, this looks very familiar, C times z minus z0 equals 0. And that will be the equation of the plane that is tangent to the surface at that point. So now the question becomes to find that normal vector, right? So how do we do it? Well, to do it, we expand on the property of the gradient that we learned in the last section, right? For a function z equals g of xy or f of xy, the gradient vector at any point, oh, so this should be f, sorry, f, because that's the gradient of f, is orthogonal to the level curve at that point. So if you look, we have different gradients drawn here, and they always are orthogonal to the level curve, right? They have to be. So I'll just make a note here. This is the gradient of f at some particular point, and it's orthogonal. In this case, it looks like it's about 1, 1. So 1, 1. Or this one up here is the gradient of f at, it looks like 0, 2. Right, because the 0 axis is actually going down the middle of this. All right, now what if it was a function in 3 variables? We can't really visualize that because you would need 4-dimensional plots, and we don't know how that would work. But we can visualize the level surfaces of the graph, right? Those are the surfaces, right? Not curves, right? So this is different. So you take a 3-dimensional object, when you do level curves, it brings it down to 2 dimensions. But when you have essentially a 4-dimensional object, right? A function in 3 variables, then they would be level surfaces. Right? And so we can visualize level surfaces. Those are the surfaces on which it's a constant, right? The surfaces on which W is constant. So level surfaces are surfaces on which W is constant. So just like the 2-dimensional gradient vector, the 3-dimensional gradient vector will be orthogonal to the surface, right? It forms this 90-degree angle. So you can see right here, this is the gradient of W, right? And it's orthogonal to the level surface. And again, we can't draw the actual object. Whatever this is, it's 4-dimensional, right? So we can't draw that, but we can draw the 3-dimensional level surface. So we can keep that in mind. So the normal vector would be the gradient of W, where W equals K is a level surface. so let's put it all together, right? To find the equation of a tangent plane to the graph of a surface, we need to find a point. At least two of the three coordinates will be given, right? Because of course, if I give you the x and the y, you could find the z if you have the function, right? So right here, I'm only giving two, but that's fine, right? So find a point. Find a normal vector by rewriting the equation of the surface so that it is equal to a constant. Note that the level surface, w is equal c, is the function where we are interested in. So the gradient of w evaluated at that point is the normal vector to the surface at that point. Right? So right here, you let w be a constant, and this will happen. And then we just use the standard form of the equation, and we're fine. Okay, so how does this work in practice? So if you look at this particular function, this is z equals, I'll write it right here, z equals natural log of 1 plus xy. Now, this isn't going to work directly into our particular problem because it's not set equal to a constant, right? We need this level surface to be w equals c, w equals a constant. So we can make it into a function w by just writing it that way. If we subtract z from both sides, w is the natural log of 1 plus xy, take away z. And I can just set it equal to 0, right? Because if I subtract it away, right, z take away z would be 0. Well, now we're cooking. Now we have this function, w, and we have a constant. So now we can find the gradient and life is grand. Oh, and for the record, it didn't have to be subtraction of z. You could also subtract the natural log, right? So you could do z take away the natural log of 1 plus xy, or you could do the natural log of 1 plus xy minus z. It doesn't really make any difference. It just makes it so that the normal vector is pointing one way or pointing the other way. Okay, so now the normal vector. Oh, let me write that as a note real quick. There we go. So either one, right? Either to subtract the z or subtract the natural log. All right, the normal vector will be the gradient of w, which will be wx, wy, wz. Okay, so I want to take the derivative of this with respect to x. And x is tricky because we have this natural log, so we would need chain rules. So we would do 1 over 1 plus xy times the derivative of the interior with respect to x. So the derivative of 1 would be 0, and the derivative of xy would be y. And then for the derivative of with respect to y, it'd be the same thing, except it'd be multiplied by x. And the derivative of w with respect to z is negative 1. Okay, so this is the normal vector at any point, right? X, Y, Z. We want the normal vector at our particular point. Well, I'm just going to say xy is 1, 2. Actually, I could go find it. Here, let's just real quick. If xy is 1, 2, then z is the natural log of 1 plus xy. So 1 times 2, sorry, which would be the natural log of 1 plus 2, which is 3. So just make a note of that right there. All right, so sorry, my 1 got weird. I was going to write x there for no reason. All right, 1 times 2. Okay, so that means I can say natural log of 3 for the back number. Sometimes you need it, sometimes you don't. We actually don't need it for this particular one, but there we have it. So this is the standard normal vector, right? This is the normal vector for all the points. We want the normal vector at this point. So that would be the gradient of w at 1, 2, natural log of 3 is equal to 2 divided by 1 plus 1 times 2. So 1 plus 1 times 2. And then 1 divided by 1 plus 1 times 2, and then negative 1. Right? Nothing special is happening back there. So that means we're saying 2 over 3, 1 over 3, negative 1. There's our normal vector. All right, so let's put it together. We have our point, right? Here's our point. We have our normal vector. And so we put them together and we say that the equation of the plane would be 2/3 x minus 1 plus 1/3 y minus 2. Take away 1, if you will, z minus the natural log of 3 equals 0. And if you want to, you could distribute and combine like terms and multiply. I would multiply everything by 3, and you can mess around with it. You would get 2x take away, or excuse me, 2x plus y minus, because if I multiplied everything by 3 to make the 3's go away, minus 3z, and it'd be equal to, bringing these to the other side, it'd be 4 take away 3 natural log of 3. Again, you don't have to do that. That's just, all I'm doing is distributing, combining like terms, multiplying everything by 3, basic algebra 1 stuff. And for the record, if you did the other direction, if you went this way with it, if you did z minus natural log, what would happen is everything would be the same, except these numbers would be opposite signs. It'd be negative 2/3, negative 1/3, positive 1. The point obviously wouldn't change because that wouldn't make any difference. And so it's fine. It'll totally work, right? So either way you like it.